Welcome to just a tiny corner of math, and this is episode 2 in my series of just interesting math problems. Now, I've decided that for every power of 2 of this series, I will do a power of 2 problem or base 2 problem, whichever you prefer. So, today we'll be tackling an interesting variation on the problem previously discussed on the channel. Now, it's very similar, right? So, very similar setup. So, we've got 1, 2, 4, 8, 16, and so on. All the powers of 2. That is our set here. And, is there a way that you can express all the numbers? I'm not going to bother writing out the question this time, but is there a way you can express all the numbers when you have to do all the numbers but alternate the signs? So an example of this would be 1 is equal to -1 plus 2, then like 2 would be -2 plus 4. Same one as last time, no repeats. 3 is when you can actually start showing the interesting things. This one could be 4 minus 1, so it doesn't matter which sign they start out in. So, yep, that is the premise of the problem. And, yeah. So, if you want to give this a try, you can go ahead and pause the video here. I'm going to wait just a few seconds. Okay, so when this problem was originally presented to me, as examples, they listed the first 8. And initially, I was a bit confused as to what they particularly chose. Whoopsie daisy. Okay. Initially, I was confused as to what they chose. And I was also a bit confused as to why they chose to express the powers of 2, i.e. 1, as -1 plus 2, and 2 as -2 plus 4. Now, turns out that that's actually fairly key to solving the problem. So, for those of you who are wondering, there's a particular reason why I did this. Of course, you could just say, oh, well, that's just 2. But a very particular hint was contained in this thing. Right. So, when going about this, I first decided that we need to reduce our workload in terms of proving this thing. So, we don't really want to put in all the effort to proving every single number. It's easier just to prove them for all the even numbers, right? That it's certainly the case. So, when I was thinking about this, I was just like, okay, if every single even number starts with a negative sign, with the exclusion of 1, but we've already proven that works, you can simply tack on a 1 in front of it. So, for example, 3 is also equal to 1 minus 2 plus 4. So, as long as we can get the numbers to work together, the even numbers to start with a -1, or not a -1, just a negative number, you can get it such that all numbers do, because you simply tack on a 1 in front. So, yeah, obviously the special case being 1, but once again, we have already shown that to be true. So, you might have another go at this problem, I guess, after giving you those 2 hints. So, you can pause the video again, I guess, but I'm gonna start diving into the solution. Okay, so these even numbers are fairly close here at the beginning, right? The only exception of not a power of 2, just very early on, even numbers would be 6. And interesting way you can do 6 is just negative 2 plus 8. Okay, and that's not that helpful, I'll be honest. It's not a very useful way of putting it, but we'll get more into that later. Now, 8 simply keeping with this pattern. I don't see a reason to break it just yet. This, okay, and it would seem as though we've hit a wall. Like, if I were to give you something such as 10, you could probably figure out something to the likeness of negative 4 plus 16 minus 2. And it seems as though for any number that you can, in fact, express them on. Now, I ended up coming up with a rather interesting solution, but one that is certainly not the most elegant, because you can quickly notice that with these powers of 2 that something's happening, and you can quickly tie it in with the previous problem. Right, so when I was doing this problem for myself, I listed a whole bunch of them, just a whole bunch, all the way up to about 30, before I really started catching on. So I highly recommend you do that, and you can rather quickly, in my opinion, come up with the solution. Okay, so something that I'd like to assert is that the distance between any two powers of 2 is always going to be less than or equal to the power of 2, the lowest power of 2. So this can be written as and I think that you could sort of come up with this, I think, fairly easily, just by observation. I can't really think of a good way to prove it, I suppose. But hopefully this fact makes enough sense. Because obviously you can consider this as 2 times 2 to the n minus 2 to the n is equal to that. And if we factor out the 2 to the n, we get 2 minus 1. And then I think at this point it's fairly easy to say that they're equal. Alright, so that's the fact that we can use to our advantage. Because if you've been listing them, which I'm sure you haven't, but just in case you have, you've probably noticed a pattern that you can find a really easy way to express all of them. And that easy way is when you have a large number, right, you first look at the power of 2 that's closest to it and simply say, oh, well, that's going to be 16. And then you simply create 16, right? And then you add another 2, which, very conveniently over here, we know is that. So, something very interesting has happened here. We notice that for all the numbers above 16, all the way up to 32, a very easy way we can express these numbers is negative 16 plus 32 plus some x, where x is a even number in the series. And as I've said, we are ensuring that the negative for every even number starts with a negative 1. So x will always be negative, which means it won't break this alternating sign rule. Now, the other key is that they can't repeat, and they're not going to repeat, mainly due to the fact that this distance will immediately put any number between 18 to 32 in a distance less than 16. And because of that, we'll never need to express 16, which means that we don't have to use these large numbers. We can use smaller numbers. Now, it won't always give the most efficient way. It's like looking back at 10, I offered the 4 plus 16 minus 2. My solution would simply say that for 10, you would first start identifying as the closest power of 2, which would be 8, so 8 plus 16, and then you need to show 4, or yeah, show 2, and then you would simply do it this way. And that makes sense. You can set these equal to each other and they work. So they don't always yield the most efficient thing, and an interesting extension to this problem is, given an integer n, what's the smallest, how many numbers does it take to express it for any given integer n? I have not figured out a solution to that problem, but maybe we'll see something similar to that on episode 4. So, as I've shown here, for these things, we will always be able to express it, and then it'll work, correct? As long as, and for those of you who notice this hitch, we can express all the ones from 16 to 8, correct? Because we know that from 16 to 8, they'll never have a difference lower than 8. And that's true, but it's also true for 8 to 4, right? Just notice how I'm simply comparing the distances between the powers of 2, and how, as long as you have all the previous numbers, we can always find that x for any given number, and we'll already have it. So, what happens here is 4 to 8, well, that's 4, but we don't necessarily know that, but we do definitely know that all the even numbers from 2 to 4 work. Because we know that, we know that all these work, and we know all these work, and basically through a sort of proof by mathematical induction, we can infer that this works, because obviously, if this works, then 64 will work, because now we have all the even integers below 32. And then, like I said earlier, if you want 11, just tack on a 1, and there you go. So, there's a solution to the problem. And the cleverer among you in the audience, the one viewer that's watching this, you may have noticed something very, very similar to my previous proof. The whole idea that since we have every base, we'll always be able to show that it works. Now, like, recalling the previous proof, right, which is simply the fact that since we have 1 and 0 for every single base operator, we can simply turn each number on and off corresponding to whatever the numbers would be. And by on and off, it's very common terminology for expressing 1 or 2 in each digit. Right, so that was the proof for last time. And those of you in the audience who happen to have realized this is basically a hidden version of this problem, because, well, I showed you earlier, 1 is equal to negative 1 plus 2, and 2 is equal to negative 2 plus 4, and 4 is equal to negative 4 plus 8, and so on. So, clearly you can see here that we can express individually every single one of the powers of 2. And that means, once again, in base 2, that we can show every single number. So that's a more creative way. That didn't occur to me for a while. But the main hiccup I had with this is, how do you know for a fact that it'll all work out? Well, I assure you that you can find solace in the fact that this starts with a negative. Oops. This starts with a negative. Okay. This starts with a negative, right? This now destroyed expression. We can now say that this also starts with a negative, correct? Which means that you'll always be able to show this. Now, you'll definitely get some rather annoying things coming up, like, for example, if you were tasked to show any number of the size 2 to the n minus 1, you'll go through a vastly inefficient way of expressing it, because even for 3, we would want to show negative 1 plus 2 minus 2 plus 4, right? That's how you'd go about it, because it'd be a 1 and a 1 in base 2, so we would simply add those two together, and we'd get this, but these cancel, so you'd have a very horrific expression here. But you'll also notice that that's rather convenient, because it'll cancel, which means that there's no repeats of the digits, which then takes care of this problem. So yeah, that was 2 clever solutions. Well, 1 not so clever. But 2 solutions to this very interesting variation on the previous problem. So yeah, once again, just every power of 2 episodes of interesting math problems will be a power of 2 question episode. So look forward to that. Bye.